If your RAG retrieves the wrong chunks because embeddings miss exact terms, hybrid retrieval is the standard fix. We'll combine BM25 and embeddings into a single score and make retrieval more stable. You might see LLMs pull irrelevant paragraphs because the embedding says two texts are close, but the query contains an exact name or task word that the embedding softened. By the end of this video, you will understand a simple Python hybrid that blends keyword weight and vector similarity into one score, and you will be able to tweak that blend to favor precision or recall. This keeps names and rare keywords alive while keeping the semantic power of embeddings. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. Hybrid retrieval answers a common pain. Embeddings give semantic generalization. BM25 or keyword methods give exact token matches. Alone, each has blind spots. Embeddings may ignore uncommon names. Pure lexical search misses paraphrases. A hybrid that scores both kinds of signal with a single number gives predictable, tunable results. In practice, this reduces missed entity hits and improves precision on FAQs and support articles. For small to medium corpora, you can do this in memory and get sub-second responses. Think of it like voting. One voter counts exact word overlap. Another voter scores how close vectors are. We normalize both votes to the same range and add them. If you want names to matter more, you raise the keyword weight. If you want paraphrase recall, you favor embeddings. A tiny example makes this concrete. 3 short documents and 1 query that mixes a name and task words. That keeps the example focused and repeatable. We will build a pipeline step by step. First, a lexical baseline. Then add rarity weighting similar to IDF. Next, a toy embedding and dot product. After that, we scale and blend both signals. Finally, we add a cheap name boost to recover entities. None of this requires a heavy library. The code uses simple functions and small vectors, so the ideas are clear and editable. Now we'll build a naive lexical baseline. This snippet ranks documents by simple keyword overlap with the query. We define 3 tiny docs and a query that mixes a name and task words. The function talk lowercases text and extracts alphabetic tokens so comparisons are consistent. The sorted call counts how many query tokens appear in each doc and orders by that count with a stable tiebreak on index. This produces a quick lexical baseline without any learned model or external library. The printed ordering shows which docs share the most words with the query, and where names already fail to compete with multiple task terms. Next, we'll make the lexical score smarter by weighting rare terms. This snippet upgrades lexical scoring using IDF to weight rarer terms. We first build D as tokenized documents, then compute IDF only for query tokens to keep it tiny. The dictionary IDF gives higher weight to terms that appear in fewer docs. The function SC sums those weights for each doc's tokens, acting like a compact TF-IDF without external depths. Finally, we sort by SC so terms like vector or search can outweigh frequent ones. The printed order reflects rarity-aware matching and often strengthens precise keyword hits. Now we'll introduce a toy embedding and rank by vector similarity. This snippet builds tiny hashed embeddings and ranks by dot product. The function M maps tokens into 3 alphabetical buckets, forming a fixed size vector per string. This simulates a low-memory embedding that groups similar initial letters. Then we use a dot product with the query vector as a simple similarity. The sorted call maximizes this similarity and uses index for a stable tiebreak. This shows a crude semantic-like signal that may favor topical overlap while ignoring exact names. The printed order demonstrates how embeddings can miss name specificity. Next, we'll blend the lexical and embedding scores into one combined rank. This snippet combines BM25-like and embedding signals into one score. We reuse SC for lexical IDF strength and compute an embedding dot product list, EM. The helper N applies min-max scaling to both lists so they share a 0 to 1 range. We blend them with alpha, where higher alpha favors keywords and lower alpha favors embeddings. Increasing alpha pushes results toward precise matches. Decreasing it can improve recall on paraphrases. The printed order shows a balanced ranking that keeps topical relevance without discarding names. Finally, we'll add a simple name boost to fix missing entities. This snippet adds an exact name boost to fix missing entities. We collect caps as lowercase tokens, seen capitalized in the corpus, the cheap proxy for names. The set names filters the query to only those candidate names. We then add a boost to H for any doc containing one of these names, preserving the single hybrid score while correcting entity underweighting. Raising the boost surfaces exact names more aggressively. Lowering it keeps more semantic control. The printed order highlights how names are recovered without discarding the hybrid signal. This toy example maps directly to a real project. Use the same hybrid scoring when you index FAQ pairs, support tickets, or internal docs. Replace the toy embedding with a real model and swap the in-memory sort for an approximate nearest neighbor index when you scale to larger corpora. Recap: hybrid retrieval blends lexical weight and vector similarity into one score. Use it when you need both exact term matching and semantic recall. Caveat: tuning the blend and name boosts matters, because too much weight on one signal will drown out the other. Next step: tune the alpha blend and the name boost on a validation set, or swap the dot product for cosine similarity in the same pipeline, and measure precision at 5. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.